Welcome to Distributed Systems from Scratch. This is episode 1. We're starting at the very beginning. Why do distributed systems exist? And why are they so hard? Imagine you've built an application. It runs on one server. For a while, everything is fine.
But then traffic grows, your database fills up. One day, that server crashes at 3 a.m. and your entire service goes down.
A single machine has finite CPU, finite memory, finite disk. It can fail, and it lives in only one physical location. So we distribute our systems for three fundamental reasons. First, scalability. Instead of buying a bigger machine, we add more machines. This is called scaling out or horizontal scaling. Second, fault tolerance. If one machine dies, the others keep serving. No single point of failure. Third, low latency. We can place copies of our data close to users. A user in Dhaka shouldn't have to wait for a round trip to Virginia. But here's the thing. The moment you go from one machine to many, everything gets harder. Leslie Lamport, one of the most important figures in this field, once said,
A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable.
that's not a joke. That's the reality. So, what is a distributed system? Formally, it's multiple independent computers that communicate over a network and coordinate their actions so that the end user sees a single coherent system. The key word is coordinate. Getting independent machines to agree on anything. The time, the order of events, who's the leader, what the current state is, that's the hard part. You already use distributed systems every day. Google search, your query hits a load balancer, which routes it to a web server, which fans out to index servers across thousands of machines. Results come back in under 200 milliseconds. WhatsApp, Netflix, even Git, they are all distributed systems. Every clone of a Git repo is a full replica. Pull, push, and merge are essentially distributed consensus, just resolved by humans staring at merge conflicts.
Now, before we go deeper, there's something you need to internalize.
In 1994, L. Peter Deutsch at Sun Microsystems compiled a list of 7 assumptions that programmers new to distributed systems always make. He called them the fallacies of distributed computing. James Gosling, also at Sun, added the 8th around 1997. Every single one of these assumptions is wrong, and every single one will cause production outages if you don't account for it. Here they are. Read them carefully. The network is reliable. Latency is 0. Bandwidth is infinite. The network is secure. Topology doesn't change. There is one administrator. Transport cost is 0. The network is homogeneous. All false. Everyone. Your network will drop packets. Latency is very much not 0. Bandwidth has limits. Networks are not secure by default. Machines join and leave constantly. There are multiple teams managing different parts of the infrastructure, and the network is a patchwork of different hardware, protocols, and configurations. Let's dig into the most important fallacy. The network is reliable. When you send a message over a network, three things can happen. 1. It arrives, you get a reply. The happy path.
2. The message or the reply is lost. You wait and eventually time out. But here's the problem. You don't know if the message was lost or if the reply was lost. Maybe the server got your message and processed it, but you'll never know.
3. The message is delayed. It arrives minutes later. It looked like a loss, and then suddenly the response appears.
Fallacy number 2. Latency is 0.
Look at these numbers. An L1 cache access takes half a nanosecond. A RAM access about 100 nanoseconds. An SSD read 100 microseconds. But a network call within the same data center, half a millisecond. That's 1,000 times slower than an SSD read. Cross region, 30 milliseconds. Cross continent, 200 milliseconds. And this is governed by the speed of light. You literally cannot make it faster. Every network call in your distributed system pays this cost. 5 sequential network hops at 5 milliseconds each. That's 25 milliseconds before any compute even happens. Here's the mental model you need for the rest of this series. Every distributed system, no matter how complex, is just nodes and messages. Nodes are processes running on machines. Messages travel between them over the network. That's it. That's the entire model. Everything will build consensus, replication, transactions. It's all nodes sending messages to each other and trying to agree on things. At the transport layer, we have two protocols to choose from. TCP is reliable and ordered. It sets up a connection with a three-way handshake, guarantees delivery by retransmitting lost packets, and delivers bytes in order. Most distributed systems use TCP. Your database connections, HTTPAP is Kafka replication, Raft consensus. UDP is the opposite. No connection setup, no delivery guarantee, no ordering. It's fire and forget, but it's fast. Gossip protocols, DNS lookups, real-time video, these use UDP because they'd rather lose a packet than wait for a retransmission. Let's look at the TCP handshake in detail because it illustrates a real cost you pay in distributed systems. Before any data can flow, the client sends a SYN packet. The server responds with SYN-ACK. The client sends an ACK, and that ACK can carry the first request alongside it. That's one full round trip of setup before the server sees your first byte. If your server is 100 milliseconds away, you've burned 100 milliseconds just establishing the connection. TCP Fast Open can shave this down to 0 round trips for peers you've talked to recently, but most connections still pay it. This is why connection pooling is critical. You don't want to pay this cost on every request. One more piece of networking infrastructure, DNS, the domain name system. Before your application can connect to db.myapp.com, it needs to resolve that name to an IP address. That's what DNS does. In distributed systems, DNS doubles as service discovery. Kubernetes, Consul, AWS Route 53, they all use DNS to map service names to the current IPs of running instances. But here's the catch. DNS responses are cached with a time to live. If a node dies and gets replaced, clients might still be pointing at the dead IP for minutes. This is a real failure mode. Now here's the single most important insight in this entire episode, maybe in this entire series. A network partition where two parts of your system can't communicate and a crashed server look identical from the outside. You sent a message, no reply came. Did the server die? Is the network cut? Did the server process your request but the reply was lost? You genuinely cannot tell. And this ambiguity, this fundamental uncertainty, is the reason distributed systems are hard. Every protocol we study, every algorithm we build is trying to make progress despite this uncertainty. Here's what's coming in the next episodes. Episode 2. We'll formalize this uncertainty with the two generals problem. We'll prove mathematically that perfect agreement over an unreliable network is impossible. Episode 3. Time and clocks. There's no global clock in a distributed system, and Leslie Lamport's solution to this is one of the most elegant ideas in computer science. Episode 4. The CAP theorem, the fundamental trade-off of distributed data. Episode 5. Consistency models, linearizability, causal, eventual, what each one actually guarantees, and when each is the right choice. Let's recap what we covered. 1. We distribute systems for scalability, fault tolerance, and latency. These are the only reasons. 2. The 8 fallacies are real traps. The most dangerous one is assuming the network is reliable. 3. TCP is reliable but slow. UDP is fast but unreliable. This trade-off shapes protocol design. And 4. The most important takeaway. You cannot distinguish a network partition from a crash. This is the fundamental hard problem of distributed systems. Everything else follows from this. That's episode 1 complete. In the next episode, we'll make this uncertainty formal with the two generals problem. and you will see why some things are provably impossible. Thanks for watching.